Namaste students. In our previous video, we have studied about different rules with the help of which we can fill the electrons in the orbitals. Now in this video, we'll study the electronic configuration of an element by using the three rules. So let's get started. Students, today we'll learn about the electronic configuration of element, that is how we can write the electronic configuration of an element on the basis of SPDEF notation. Before writing the electronic configuration of different element, first of all we have to know the meaning of the term, that is electronic configuration. So what is electronic configuration? Electronic configuration is the arrangement of electrons in different shells, subshells and orbitals of an atom is known as its electronic configuration. So what do you mean by electronic configuration? Electronic configuration is the arrangement of elements in different shells, subshells and orbitals of an atom is known as electronic configuration. Now, by keeping three rules in our mind, what are those three rules? We have studied in our previous videos. I hope you studied those rules. By keeping in mind those rules, that is Abhau principle, Pauli exclusion principle and Hund's rule of maximum multiplicity. By keeping these three rules in our mind, we can write the electronic configuration of any element. If we talk about in general view, in general, the electronic configuration of any orbital can be simply represented by a notation that is NLX. The electronic configuration of any orbital can be represented by a simple notation and that notation is NLX. So NLX is a notation which is used to represent an orbital. An orbital where n is the principal shell and L is the subshell. Suppose I am talking about 3D5. So 3 means third shell, D means D subshell and 5 represent the number of electrons. 5 represent the number of electrons which are present in this particular orbital. So electronic configuration is the arrangement of electrons in shells, subshells and orbitals of an atom. That is electronic configuration. And if we talk about how we will write the electronic configuration, by using or by keeping the three rules in our mind, that is Abhau principle, Hund's rule of maximum multiplicity and Pauli exclusion principle. And if we talk about an orbital, the electronic configuration of an orbital can be simply represented by a notation and that notation is NLX, where N represent the shell, L represent the subshell and X represent the number of electrons which are present in that particular orbital. Now we'll write the electronic configuration of first 20 elements of the periodic table. So students, take out your pen, take out your notebook and write the electronic configuration of first 20 elements along with me. And I feel happy if you write the electronic configuration before than me. The first element which is present in the periodic table is hydrogen. Now in hydrogen we have one electron. Now if we kept Abhau principle in our mind, according to Abhau principle, the lowest energy orbital is 1s. So the first electron will enter in 1s because according to Abhau principle, the electrons will fill in the increasing order of their orbital, increasing energy order. It means lower energy orbital will fill first and higher energy orbital will fill later on. So hydrogen, the number of electron are 1. So the electron will fill in 1s. Now S, we know that in S the value of ml for s in quantum number. Now again we have to recall the quantum number in our mind. In quantum number we have studied that for s, L is 0, means azimuthal quantum number is 0, and ml is also 0, means there is only one rotation, only one orientation for s, and if one orientation for s, it means only one orbital. It means s, we have only one orbital. And if we talk about Pauli exclusion principle, in Pauli exclusion principle, it is clear that in an orbital we have only 2 electrons. There is an accommodation of only 2 electrons for a particular orbital. In s, we have one orbital and there is a place for only 2 electrons, but in hydrogen we have only 1 electron, so 1 electron will enter here, so configuration becomes 1s1. Clear? Now helium. In helium we have 2 electrons, so again the first electron will fill in 1s, but the second electron will also fill in 1s because there is a place for 2 electron in 1s. So the configuration becomes 1s2. Now the third one is lithium. Third one is lithium. In lithium we have 3 electrons. So the first electron will fill in 1s. Second electron will also fill in 1s because there is a vacancy for 2 electron, but there is no place for third electron. So third electron will move in that orbital whose energy is greater than that of 1s, and if we recall above principle, the orbital whose energy is greater than 1s becomes 2s. So it is 2s1. So the configuration becomes 1s2, 2s1. If I talk about beryllium, in beryllium the number of electrons are 4. So the configuration becomes 1s2, 2s2. Clear? Now if I talk about boron, in boron the number of electrons are 5. Now write the electronic configuration of the boron and give me your answer. I'm waiting for your answer. Now next is carbon. Next is carbon. In carbon the number of electrons are 6. The number of electrons are 6. 1s2. Still we have 4 electrons. The next orbital become 2s, and 2s we have place for only 2 electrons. So 2 electrons will pair. Still we have 2 electrons. Now it will move to the next higher orbital, and if we remember above principle, it's 2p. So 2p2. So the configuration becomes 1s2, 2s2, 2p2. I'm still waiting for boron configuration. Students, I'm still waiting for boron configuration. Nitrogen. In nitrogen, the number of electrons are 7. So configuration becomes 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. Next is oxygen. Now, in oxygen, if I'm talking about in oxygen we have how much electrons? We have 7 electrons. So it becomes, we have 8 electrons. In carbon we have 6, in nitrogen we have 7, in oxygen we have 8. So 1s2, 2s2, 2p4. Next one is fluorine. We have 9 electrons. So 1s2, 2s2, 2p5. Now why I'm adding electrons again and again in p orbital? Because in s orbital I'm adding only 2 electrons, but in p I'm adding 3, 4, 5. Why? Because for p L is 1. For p L is 1 means for p azimuthal quantum number is 1. If azimuthal quantum number is 1, then magnetic quantum number becomes -1, 0 and +1. It means we have 3 orientation. If 3 orientation is there, it means we have 3 orbitals. And if we have 3 orbitals, we have a place for 6 electrons because 2 electrons can accommodate their place in 1 orbital. So 3 orbital means 6 electron. That's why I keep on adding the electron in p orbital till then the p becomes 6. So next is neon. Now the atomic number of neon is 10. So the electrons are also 10. 1s2, 2s2, 2p, 6. So this is the electronic configuration of first 10 elements. Now we'll write the electronic configuration of next 10 elements. But still student, I am waiting for your answer. Now after neon, we have sodium. The atomic number of sodium is 11 and the number of electrons are also 11. Now we'll write 1s2, 2s2, 2p6. Now above principle after 2p, because here 2p is 6 means fully filled, because in p we have 3 orbitals and 3 are completely filled. So 1s2, 2s2, 2p6, still we have 1 electron which we have to fill in that particular orbital. So the next higher orbital becomes 3s. It's 1. Or you may also write the electronic configuration like neon 3s1 in term of noble gas configuration. Because neon is the noble gas which is present before sodium. So you can write neon and then neon, the configuration of neon is this. It means neon represents this configuration and 3s1. So either this form or this form. Both the form are correct for sodium. Now if we talk about magnesium. In magnesium, the number of electrons are 12. So the configuration becomes 1s2, 2s2, 2p6, 3s2. 2p6, 3s2. Next, aluminium. Aluminium is 13. Clear? 1s2, 2s2, 2p6, 3s2, 3p1. Clear? Okay? 1s2, 2s2, 2p6, 3s2, and after 3s, above principle, yes, and after 3s we get 3p as higher orbital, higher energy orbital. Sodium, magnesium, aluminium, then silicon. Silicon is 14. So becomes 1s2, 2s2, 2p6, 3s2, 3p2. Then 15th is phosphorus, yes. And I hope you are writing the electronic configuration of phosphorus faster than me. 1s2, 2s2, 2p6, 3s2, 3p3. Next one is sulfur, that is 16. 1s2, 2s2, 2p6, 3s2, 3p4. Or we can also write in terms of noble gases. Neon 3s2, neon 3s2, 3p1, neon 3s2, 3p2, neon 3s2, 3p3, neon 3s2, 3p4. Now we'll write the electronic configuration of next four members, that is 17, 18, 19 and 20. Chlorine 17, 1s2, 2s2, 2p6, 3s2, 3p5. 2, 4, 10, 12, 12 over 5, 17. Now, or neon 3s2, 3p5. Next is argon. Argon 18. It is 1s2, 2s2, 2p6, 3s2, 3p6. Clear? Or neon 3s2, 3p6. Now we'll deal with potassium. Potassium is 19. Now 19 means 1s2, 2s2, 2p6, 3s2, 3p6. Now where is the last electron will go? Now if we talk about first shell, in first shell we have S subshell and one orbital. In second shell we have S as well as P subshell. Clear? In first shell we have only S subshell. In second we have S as well as P subshell. In third we have S, P and D subshell. And in fourth we have S, P, D and F subshell. So it is obvious after 3P 3D will come. But we studied in above that before 3D 4S will fill. Why? If I'm talking about 3D, if I apply N plus L rule here, here the N is 3. Here the N is 3 and D is also 3. D is also 3. Sorry, D is here 2. N is 3 and D. L 0, 1, 2. 0 means S, 1 means P and D means 2. So N plus L becomes 5. And if I apply N plus L rule for 4S, N is 4 and S is 0. So it becomes 4. And we know that lower the value of N plus L, lower is the energy. And electron will go in that orbital first whose energy is lower than the other. It means energy of 4s. Energy of 4s is less than 3D. So electron will go 4s and then will go in 3D. So it becomes 4s1. It becomes 4s1. So electron will not go in 3D, it will go in 4s1. So 3D becomes 0. Or the configuration becomes argon 4s1. That is clear? Due to the energy difference, the electron will move in 4s and then move in 3D. Means when the electron will fill in 4s, when the electron becomes 2 in 4s, then the third electron will move in 3D. But first electron will move in 4s instead of 3D. Now if I talk about calcium, calcium, it's 20. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 or argon 4s2. So here also the electron will first move to 4s, means enter in 4s, and when the 4s will fully fill, then the electron will move to 3D. Though the 3D is in third shell or third subshell, but still due to the less energy of 4s, the electron first fill 4s and then 3d. Now here we have two exceptions, and these two exceptions are important also. These two exceptions are electronic configuration of chromium and copper. Now try to write the electronic configuration of chromium. Try to write the electronic configuration of chromium just like this, as we write the electronic configuration this. So it becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Obviously, clear? Up to 4s2, the number of electrons are 20 and we have 24 electrons. So the 4 electron will move to next energy orbital, and next energy orbital is 3d. Means the energy, the orbital whose energy is greater than 4s is 3d. So the electron will enter in 3d orbital. So the configuration becomes this. Correct? Configuration becomes this. How many of you have written the configuration like this? I hope all are writing the configuration like this only, because if you are writing the configuration like this, it means the above concepts are clear to you. But here we have an exception. Instead of this, the configuration becomes, this is the wrong configuration. This is the wrong configuration. The correct configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. This is the correct configuration. Though according to above rule, this configuration is correct. Clear? So if as a student you are writing this configuration, it means the above concept is clear to you. But this is not a correct electronic configuration or electronic representation for chromium. This is the correct one. Similarly, if I'm talking about copper, if I'll talk about copper, in copper, the number of electrons are 29. So configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d9. Okay? 2, 4, 10. Here it is 20 and here it is 29. So 29 electrons will fill. First 4s, then 3d. But this is also wrong. The correct configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. This is the correct configuration. So there are two exceptions. One is the chromium and another one is the copper. In chromium, in place of 4 electrons in D, we have 5 electrons in D and 1 electron in S. And in copper, we have, instead of 9 electrons in D, 10 electrons in D and 1 electron in S. Now we'll study the exceptional behavior in the electronic configuration. Why the exception is there? What are the reasons behind this exception? Now we have two reasons behind this exception. One is the symmetrical distribution. Now in chemistry, when we are talking about chemical bonds or we are talking about the constituent particles, arrangement of the constituent particles, there is a well-known fact that symmetry leads to stability. Symmetry leads to stability. And not only in the chemistry, it is also applicable in your life, students. If you are symmetrical, if you are continuous in your study, then no one can able to stop you. No one can able to stop you to achieve your goal. So symmetry leads to stability. Symmetrical distribution, there is a well-known fact that symmetry leads to stability. Now, if I talk about D4 configuration, if I'm talking about D4 configuration, in D4 configuration, the configuration, if I arrange the electrons, this is the arrangement. And if I'm talking about D5 configuration, now student, tell me that out of these two configurations, which one is appeared more symmetrical? This one, because we have 5 orbitals and in all the 5 orbitals we have 1 electron. Suppose we have 30 students in our class, and these students will give these students one chocolate. So there is no problem in the class. And suppose I am giving 2 chocolate to one student and 1 chocolate to another one. So there is a thinking in the another one that why the teacher will give 2 chocolate to the other one or only 1 chocolate to me. So it means out of these two, this one is more symmetrical, means this one is more stable, this one is more calm. That okay, we have 5 different orbitals and all the orbitals have 1 electron. So symmetry leads to stability. So in chromium, before we have D4 and S2. Clear? Now D4 and S2. In D we have 5 orbitals and we have 4 electrons. In S we have only 1 orbital and we have 2 electrons. Now suppose if 1 electron will shift here, what will happen? D5 S1 means both are half filled. It means 5 orbital, 5 electron, 1 orbital, 1 electron. It means all are satisfied. So this one is more symmetrical as compared to this one. That's why this one is more stable as compared to this one, and that's why we get the exception in the electronic configuration. Now the second factor is exchange energy. Now also there is another fact that energy increases, stability decreases, or energy decreases, stability increases. So there is an inverse relation between energy and stability. There is a direct relationship between symmetry and stability. Symmetry increases, stability increases. Symmetry decreases, stability decreases. But there is an inverse relation between energy and stability. Energy increases, stability decreases, stability increases, energy decreases. So what is exchange energy? Whenever the electrons exchange their position in a particular orbital, degenerate orbital, I am talking about degenerate orbital, because in degenerate orbital we studied that in degenerate orbital the energy remains same in the ground state. So the electron with parallel spin can able to exchange their position. The electron with parallel spin. It means if the 2 electrons they are moving clockwise, then they can exchange their position. They can able to exchange their position. Suppose if 1 electron is moving clockwise and another electron is moving anti-clockwise, they cannot able to exchange their position. So the electrons with parallel spin can exchange their position, and at that time the amount of energy released is known as exchange energy. So basically exchange energy is the released energy. Exchange energy is the released energy. Now if energy releases, then the energy of the system decreases, and if the energy of the system decreases, its stability increases. So exchange energy, what is exchange energy? The electrons in a degenerate orbitals, if they are present in the parallel spin, they can change their position, they can exchange their position, and while exchanging, they'll release the energy, and that energy is known as exchange energy. more the exchange, more is the release of the energy, and more is the release of the energy, lesser is the energy and greater is the stability. Clear? More the number of exchange, more release of energy. More release of energy means less energy of the system, and less energy of the system means greater is its stability. Now, if I talk about D4, now in D4, if I am talking about the number of exchange, 1, 2, 3, 4. Clear? This will exchange with this or here, means it will go here, it will come here, one exchange, or with this or with this, means this electron can show exchange with these three. So number of exchange becomes 3, or 1, 2, 3, 4, 5. 1, 2, 3, 4. This here, here, this here, and here. Clear? In first electron will undergo 3 exchange. The second electron will undergo 2 exchange, and the third electron will go 1 exchange with the fourth one, because with second and third it already exchanged its position. So here the number of exchange becomes 2, here the number of exchange becomes 1. So the total number of exchange becomes 6. When we have D4 configuration, the total number of exchange becomes 6. Now suppose we have D5 configuration. 1, 2, 3, 4, 5. 1, 2, 3 and 4. 1, 2, 3 and 4. 4 exchange, or 1, 2, 3, 4. 1, 2, 3, 4, 5. First electron will undergo exchange with each and every one. Now second will go with fifth one, fourth and third. Clear? Here the number of exchange becomes 3. Now next one, the third one with fifth one as well as with fourth one, the number of exchange becomes 2, and 1, 2, 3, 4, 5. Fourth and fifth also undergo exchange, and the number of exchange becomes 1. First electron will undergo exchange with the 4 one, so the number of exchange becomes 4. Now first and second already exchanged their position, so second will show exchange with these 3, because this I have counted here, this exchange I have counted here, so I will not count here this exchange. 3, then 2, then 1. So the total number of exchange becomes 10. So when we have D4 configuration, the number of exchange 6. When we have D5 configuration, the number of exchange becomes 10, means 4 more exchange. If 4 more exchange means 4 times more energy is released. If 4 times more energy is released, it means 4 times less energy is present in the atom. And if 4 times less energy is present in the atom, so means 4 times more stability is there in the atom. And because of these two reasons, in chromium and copper, in place of D4, D5, and in place of D9, D10 configuration is there. So the exception in the electronic configuration in the copper and the chromium is due to the symmetrical distribution and the exchange energy. So students, that's all for today. Write electronic configuration by your own, and if you have any problem, then tell your problem in the comment section. I'll see you in my next video with new topics.